So let's get started. It's a great joy to welcome Madhu Sudan to the Triangle. Madhu is professor of computer science, the Fujitsu professor of computer science at MIT, and director of the CS and AI lab there. Associate director of the CS and AI lab there. He got a promotion, he didn't know it. An all-round very smart person who's going to be telling us some very interesting things from theoretical computer science, computation, and communication, unifying theory. Madhu, please.
Thanks a lot for inviting me, Sanjay. So I have the mic turned on, but can people at the remote locations hear me? And can someone let me know? Wave if you do. Okay, great. Thank you. I'm going to talk to you about communication and computation. And I must confess, this is not a theory talk, but I am a theoretical computer scientist. So it's a theory-influenced talk. And I want to tell you a little bit about what the theory tells me about how the interaction between communication and computation should go. I'll start with a little bit of a history. So, of course, as we all know, the theory of computing owes its computation sort of owes a lot to Turing and his proposed, I would call it, architecture of a computing machine, which involves a finite state control, reading and writing from some infinitely long tape, and acting on it. And it was I would suspect it was a sort of a remarkable model to try to think of, to say, well, what is computation? It should be encapsulated by very simple, finite amount of control, along with some infinite capability, just to make sure that you're not sort of a priori bounded in what you can do. Now, this, you may or may not realize this, but I think it had a deep influence on the practice of computation. The fact that this is how our first model of a mathematical model of a computer was proposed did have a deep create deep impact. In particular, one of the main contributions of Turing was this notion that this finite state control could be a particular universal machine which he designed, and now you can basically program anything else you want by putting in encodings of other Turing machines on your tape, and thereby one single machine sort of solves all your problems of the world. Now, this sets us apart as a discipline, computer science, from any other engineering discipline. Mechanical engineers do not have a universal machine. Electrical engineers do not have a universal electrical object. There is no single molecule which can solve all your chemical problems, but there is a single computer which does solve everything else we want. And it did influence our practice, because von Neumann did, I would presume, was influenced by it, whether he realized it or not. He was very much aware of Turing's work and his thing, and he led to this architecture where instead of calling it a finite state control, he called it the CPU. Instead of calling it an infinite tape, he had a general RAM put in over here, but then other than that, not much changed. And instead of having, this led to our stored program architecture that we sort of started implementing and building upon, and deeply influenced our theory. Now, the flip side of the theory that I want to talk about is the theory of communication. Shannon came up with this architecture for how it means to communicate reliably across a noisy channel. This is a theory that dates back to 1948. Between 44 and 48, Shannon was developing this theory, eventually published a paper in 48. And the noisy channel takes some sequence of symbols y, produces some sequence of symbols y hat, which is slightly different from what y was. And what Shannon proposed as an architecture over here was, he said, well, in order to send some message m, what you should do is encode it, and then send the signal y, which is the encoding of the message m. When you receive the signal y hat, which is not quite the same as y, but presumably close enough, you should try to decode it so that hopefully you recover the original string m. Exactly. It's not good enough for us to recover some approximation to this. It has to be exactly recovered. And this became a model of reliable communication. For the purpose of this talk, by the way, I mean, to me, storage and communication are the same concepts, okay? Storage is just communicating across time, and communication is communication across space, okay? So these are just the same concepts for me, and so when I talk about communication, I mean it in this general sense. Now there's a very interesting interaction between Turing and Shannon. Turing on the one hand assumes perfect storage, this infinite tape, assumes perfect communication, which is the ability to read and write from this tape and load these messages into the control in order to get computation. Shannon on the other hand assumed computation, there should be an encoder, a decoder. In fact, if you look at the encoding and decoding that Shannon thought about, these were really, really complicated computational tasks. These were not simple functions. He never assumed that he would be sort of restrained by the things that he could actually build in hardware. Assumed the most general forms of encoding and decoding possible to get reliable storage and computation and communication. So this is a remarkable chicken and egg problem, and fortunate. It was really, I think, it's a fortunate coincidence for us. The world we live in today manages to use the fact that we can actually get decent amounts of storage and communication capacities and decent amount of computation, which allows us to go through the cycle and make both of them better and better, and eventually we just live with it perfectly well. Yes, question?
So I don't understand where the communication really comes in Turing machine. We're not talking of it being distributed inherently.
No, I mean, but even if you want to communicate across a sort of a millimeter or less of distance, that's communication. If you try to do this in, say, so just think of the analogous world today, classical computation being replaced by quantum communication and computation. If we could really build a good quantum storage device and a quantum communication device, we would have quantum computers. And the only bottleneck, as far as we can see, is that somehow we haven't been able to bootstrap this process. We know how to do this implication, to get good storage, from good storage and communication to get computation, and from good computation to get storage and communication, but we don't know how to start the process off anywhere.
But in your duality, you're assuming that Shannon, you're saying the Shannon's computation is complex. But is Turing's communication noisy?
Any physical medium of communication is noisy. That's the Shannon axiom unstated. Everything is noisy. You can never get perfect. If I could get perfect communication, then I would not be communicating to you with finite number of bits per second. I would communicate infinitely many. So that's, I think, the thing that makes it really fundamental to our...
So going back to Shannon, so what do you mean to get reliable storage?
Again, the ability to be able to store some bits of information and reliably recover it after a finite number of units of time. One bit of information, I want to put it on some piece of device. After 1 unit of time, I want to be able to probe the device and get back. That's okay. So I would say that these two theories, whether we like it or not, have deeply influenced our practice. And today our practice has run way ahead of the theories, I think. The theory is still trying to catch up, because in the practice today, well, we have all of these computers, and they're all interacting with each other in various ad hoc ways or maybe reliable ways. And they're constantly communicating with each other, and there's a huge amount of diversity between what these systems are doing. There's a diversity of what kind of resources are available to each one of these players and what they're doing. There's a diversity in terms of the kinds of assumptions that they're making about the universe and what kinds of protocols they are working with. There's a diversity in terms of what each one of these things is trying to achieve. And there's a diversity in terms of what these people are interested in. I'm happy to cooperate and let you learn some things from me, provided it doesn't influence some deep privacy concerns or some deep security concerns. So there's concerns, there's a diversity in each one of these aspects, and that has made our theory somewhat sort of, brings up new challenges to our theory. And these are mostly challenges that I'm feeling for communication, from the communication perspective. Computationally, of course, there's a huge collection of other challenges, classical things that we haven't been able to understand. But even communication has become much more complex. In particular, I want to talk to you about 3 different nuggets over here that we have encountered and are trying to influence with some theoretical ideas. But this is just, these are just 3 things that we happen to have worked with. It's not a universal listing. So one thing that I'd like to say is that the channels of communication that we are thinking about are becoming much more complex. It's no longer a single wire which is trying to communicate between the two of us, or a single end-to-end communication thing. It's really, there's a whole network acting as a communication channel in many scenarios today. And since they're composed of many smaller ingredients, some of these are actually potentially clever, they may be potentially malicious, and the nature of errors is changing fundamentally. And this is something that I want to talk about in the rest of the talk. There's also a question that the scale of information that is being stored or communicated is much larger. And there is a constant paradox in the Shannon theory which asks the question, does scaling enhance reliability or not? Or does it actually decrease reliability? And this is something that I want to get back to given the current nature of the scaling that we're looking at. And finally, I mean, both of these I think are interesting questions that are in the intersection of maybe communication and computation, but doesn't necessarily require a merging of the theories. Just requires a little bit of an awareness of each other. But the final question I think sort of inherently requires some merging of the two theories, and I want to talk to you about it, which is the notion that, meaning of information. Information is not a dry collection of bits. It's really something that we intend to use to communicate certain intents. And I want to understand what that means when each one of these entities, the computational entities, may be constantly evolving and changing their understanding of what bits mean. So I want to talk to you about these three vignettes, and let me start with the first one. The first one of these is the sort of the most well-developed, clear mathematical theory. And here we have very nice results. In the other two, it's mostly ongoing work maybe, and some questions that I'll be raising, and some very, very partial answers. Okay? So modeling of errors. So let me start with this notion of how do you model an error? And this is a question for which there is no unique answer. In fact, the literature, starting from its very beginnings, had two very different notions of what it could mean, how one should try to model errors. There is Shannon's theory from 1948, but deeply intertwined with him was Hamming's theory, which was first published in 1950, but doesn't mean that it was later. I mean, it was really these two both influenced each other. Now, let me apply it to what's called a query channel. Okay, query channel, it's a channel that's capable of transmitting a collection of letters, elements from 1 to Q. Okay, so imagine letters of the English alphabet A to Z are being communicated. And so if you feed into this channel an element string over this alphabet from 1 to Q, it outputs an n element string from the same alphabet 1 to Q. You can think binary, but it's nicer to think much larger than binary because the numbers will be much clearer that way. Now, in Shannon's theory, the very important sort of the foundational assumption is that the errors are somehow random, somehow stochastic. And one simple model over here, and this is not the only one, but the basic simple case setting here is, so let's assume that P is the error probability. And what that means is, when I look at the ith coordinate of this n element string, y sub I, it will equal y hat sub I, what the receiver receives, with probability 1 minus P. Okay, so if you think of P as being, say, 10%, with 90% probability, the receiver receives what you send. And with the remaining 10% probability, you receive a uniform element which is not equal to what was sent. Okay, does that make sense? So this was Shannon's model, and this happens for each coordinate independently of any prior thing. This is a very simplistic setting within Shannon's theory, but this is pretty much prototypical. Everything else is sort of variations on this theme. Now this is a very clean, simple model. Hamming, on the other hand, considered something which was very dramatically different. He said, well, let's assume, I don't want to assume there's randomness and independence and so on. Let's assume something which is much more malicious. The errors are introduced by an adversary, except the adversary is bounded, can introduce P fraction of errors, can take an arbitrary subset of P of the symbols that are being transmitted and change them in an arbitrary way. And how all does this differ? Well, in this case you would say, okay, arbitrary means what does this adversary know? Well, maybe the adversary knows what message you're sending, he knows what encoding you're going to use, he knows what decoding you're going to apply. And based on all this, comes up with the worst possible pattern of errors. Okay? So it's a very, very pessimistic model, but that's what he studied. And now you can say, so what were the kinds of results that these theories obtained? Well, in Shannon's theory, it turns out that you can actually decode from a very, very, very large fraction of errors. The fraction of errors that you can deal with is, if you think of Q as going to infinity, a very large alphabet, The proper fraction of errors you can deal with is more or less 100%. I mean, you can deal with a very, very large fraction. The exact number is that much. So if you have an alphabet of size 26, then 1 minus 1 over q is like 25 over 26. So every 24 out of 26 symbols may be getting corrupted when you're transmitting over the English alphabet, but that still leaves you with a positive correlation between what is being transmitted and what is being received, and that positive correlation suffices for reliable transmission of information. You may think that this is a sort of a very perverse, bizarre setting. Why would you ever care about these things? But actually these are the models that turn out to be extremely useful when you deal with satellite communication. You have a very low power satellite out there transmitting signals back to Earth. Now, the correlation between the signal and what's being transmitted and what's received is very weak, but it's positive. And so the Shannon theory applies and tells us that you can communicate successfully. What about in the Hamming setting? Well, if the errors are adversarial, I could take your valid sequence that you're trying to send, replace it by my own sequence, and superpose my sequence 60% of the time. How is any receiver supposed to figure out that the sequence that they're saying 60% of the time is not the right signal? So clearly 50% is the maximum limit of such the amount of errors that one can tolerate, and so the error probability can never exceed 50%. So this was the Hamming theory, that was the Shannon theory, and which was the right model? Well, 60 years of wisdom seems to be translating into saying that you can tune the error model, you can always build the right collection of combinatorics to figure out what should the encoding do, algorithms to figure out what the decoding should do, and some probabilistic models to make sure that you're always capturing all the channels so that the Shannon model works. Okay. So this seems to be great. This is correcting, basically the maximum possible fraction of errors and corrects much more than the Hamming setting, except that, this is a very, very optimistic modeling of the channel, and I find that, increasingly I worry more and more about it. And the question is, was there any alternative? And it turns out there was an alternative. It's a theme called list decoding, which was proposed actually by Elias also in the 50s, 1956. And what this theory says is, well, let's weaken our decoder to do the following. Instead of saying, look, this was the message that the sender probably was trying to send, let the decoder output a small list, M1, M2, and so on, let's say 100 possible messages. I think one of these is probably what the sender was trying to send. And let's say that we'll just call this successful if this list of 100 things includes the message. Okay? And now let's try to correct p fraction of adversarial errors under this model. Okay, what will happen? Well, first thing that turns out is that if you take all the 60 years of wisdom and everything that we did over here, it would say that this is good enough in the sense that if there was ever a probabilistic model that could have been retrofitted to your channel and algorithms and combinatorics could have all been built, it would end up saying that this list will contain one element. Okay, so it doesn't matter what you're. On the other hand, the algorithmic challenges are fixed independent of what the channel is. It always says, ask this decoder to produce a list of all the things which are represent the fact that p fraction of the symbols have been corrupted by an adversary. And let's try to find out what they are. And so there's this alternate model that works, and one of the things that was realized in the Russian literature in the 70s, I don't have precise references in this talk, but you're welcome to probe me for this later. The Russian literature said that, well, in this model, if you could solve this problem, then you're effectively correcting as much adversarial errors as you could correct in the Shannon model. So the Hamming model and the Shannon model end up merging if you just relax your decoder to produce a larger list. Okay? It was the bottleneck of saying which was the most likely message that was the bottleneck. Yes, Sanjay?
So is L given to you, or?
L is not given to me. It depends how close to the optimal capacity I want to get. If I want to be within 1% of capacity, that says L would probably need to be something like 10,000. Okay, so there's a distance, how close to the optimal capacity, to the Shannon capacity do I want to get? That tells me how large this list size is. And this list size grows in a relatively benign sense compared to how large the messages have to be even in the Shannon model to get that close to capacity. So these are really very realistic, very reasonable things. So you basically say, how close do I want to get to capacity? That tells you how large the list size you should be willing to tolerate. But by and large, none of this matters if any of this wisdom was correct, because then it implies that this list will have one element. Your algorithm is built to produce a large list, but the errors are not going to be able to find all those other weird patterns of errors which will force this list size to be large. Okay. So this was the story of list decoding. So you might say, why didn't we just employ this through all these years? After all, this is a much safer model of errors. I mean, if an adversary is allowed to inject errors and we can correct them and live with that, that's great. It turns out that this is algorithmically a very challenging problem. Okay. The thing is, correcting a few errors is already, a really hard problem, has all sort of NP hardness might rear its ugly head somewhere out here. Even correcting, 10% errors is hard. What about correcting 70%, 80%, 90% errors? Turns out to be getting harder and harder, and especially so when the adversary injects it. Notice that in these cases there's more errors in the information than data. Error correction was mostly viewed as a problem of, removing the small few, dirty bits. And now here we're looking at this thing and we're saying, okay, everything is dirty, now where's the clean part? And that's the kind of questions that we're asking. It was inherently considered hard. And in fact, nobody seems to have really looked at these things till the late 80s. And finally, Goldreich and Levin, a couple of cryptographers, complexity theorists, raised this question of, can we try to do some list decoding for interesting codes? They gave, in fact, a very non-trivial algorithm for a very non-trivial but weak code. And they already said, well, once you can do these kinds of things, you guys have all sorts of applications in other fields. I won't tell you about those. But that started raising our awareness of these questions. And so I started looking at some of those questions in about 96, and then with a student, Guruswamy, we gave a list decoding algorithm for what's called Reed-Solomon codes. Now, I won't get very theoretical in this talk, but I'll try to tell you a little bit about this just because I love this result. It's a very clean problem and an algorithm, which I'll tell you about in a few minutes. And what we were able to do was take any fraction of errors, p, anything which is less than 100%, and we were able to consider a channel which would have p fraction, introduce p fraction of errors, and pump information through it at some positive rate. Okay, so if I'm going to have to deal with 80% errors, I can't possibly push information through this channel at 100% rate. I probably have to at most 20% is the rate at which I should be able to work with. Our results maybe said something more like you could use it at 4% rate, not 20%. Eventually this led to a lot of very nice algorithmic innovation. A lot of different people in both the computer science community as well as the electrical engineering and based coding theory community got into this thing. They started giving algorithms for very many very interesting problems, and this theory reached a very, very nice successful conclusion lately. I won't be able to tell you about these results. What they're able to do is really give list decoding of a variant of these Reed-Solomon codes. I haven't told you what Reed-Solomon codes are. I won't tell you what the variants are. But they were able to correct any fraction of errors that you want to specify with the optimal rate. What is the optimal rate? If there is 80% error, the rate that you should expect to be able to transmit is 20%, and they could get arbitrarily close to 20%. So that's the kind of results they were able to get. So in what's coming up in the next 2 or 3 slides, not too much, I'll try to tell you what is this Reed-Solomon decoding problem and how you can actually solve some of this algorithmic list decoding problem just by pictures and so on. Okay? So trust me, I won't tell you what the code is, but this is what the decoding problem is. And it's a very simple geometric problem, and I think many of you will be able to understand what the problem is even if you don't know why it's related to list decoding. Okay? The problems over here is a very simple polynomial curve fitting problem. You're given a bunch of n points in the plane. This plane happens to be actually over finite fields, which will get rid of some numerical analysis issues that you might otherwise worry about. But for conceptual simplicity, you can just imagine that these are just rational points on the plane. Okay. So x1, y1, x2, y2, and so on up to xn, yn, n points in the plane are given. I give you two parameters, k and t. K is the degree and t is the agreement parameter, and I want to find all degree k polynomials that pass exactly through t of these points. Okay. And why is this potentially a hard problem? I mean, I have formal definitions in purple, but ignore them. The big font is all you should worry about. So why is this an non-trivial problem? If k is somewhat large, then the brute force algorithms, I can think of two of them, one of which will say, let's try to find out which subset of t points work, but then I have n choose t possible choices of this subset, and that's exponential in n or t. The other algorithm might say, well, let's try to enumerate all the possible degree k polynomials through these things, but there's about n to the k of those also, both of which are exponential in the parameters k and t, and what we would like to find is a better algorithm. So I'll warn you that this is going to be an algorithm which will, this is really a polynomial passing exactly through a point. It's not an approximation. That's a very different problem, and I don't know how to solve it. So this is a very interesting problem. I'll tell you a little bit about its history. I'm sorry I don't have it on the slides. This is a problem that apparently we knew how to solve in 1960. Okay, before, in polynomial time, provided t was very large. Okay, t had to be much larger than n over 2. But still, you know, that's a non-trivial problem. Even if you say I'm willing to tolerate only 10% errors, and so t is going to be 90% of n, and k may be, let's say, n over 2, I don't know how to solve this problem easily. And this is not a problem that I can give to a undergraduate taking a course in algorithms and say, hey, come up with an algorithm for this thing. So but we knew how to solve this problem, and when I was in grad school, I used to sort of constantly invoke the fact that this is a problem that we know how to solve in polynomial time. And Manuel Blum, who is one of our faculty members there, said, this is not a satisfactory answer. If you really think that this is a fundamental problem, you should know how to find this solution in polynomial time. It's not good enough for you to know that something can be done efficiently. It's not good enough to know how multiplication is done efficiently. You have to be able to multiply. Similarly, if you think that this thing can be done efficiently, you should at least make an effort and try to find out how it's done. So I did, and it took me about 2 years to find out how this problem was solved in the 60s. And it was non-trivial because, the algorithms get encrypted over time, and, there were lots of deviant, lots of subtleties which were not clear what role they were playing, and eventually turned out they were not playing any role at all. They were just there to confuse the reader. And eventually and another 5 years passed after I graduated before I could figure out how to improve upon it. And the improvement, I feel, actually simplifies some of the explanation. So let me try to tell you what our new algorithm looks like. Okay, I'll tell you this algorithm by example and pictures. Okay, so here is a very simple version of the problem. I'm going to simplify things dramatically by assuming that I want to solve the problem when k equals 1. K was the degree. So a degree 1 polynomial is a straight line in the plane. So it's much easier. In fact, you can all think immediately of quadratic time algorithms which will solve the problem. But I want to give you an algorithm which actually scales nicely with k. And so here I'm going to try to find, I'm given n points in the plane, n is 14. Each one of these circles is actually a point. T is 5, which means I want to find lines which pass through 5 of these 14 points. This roughly corresponds to saying that I'm allowing 9 errors out of 14. There's more errors than real data. 5 real data points, 9 errors. So there is a case where, yes, the errors are overwhelming, but they're not going to overwhelm us. We'll still be able to find it. One of the nice things about lines is that you can actually find them. And here's a line, actually, which has 5 points through it. Okay. There's another line that you can see which has 5 points going through it. And a good question is, are there any other lines? Anyone see any other lines which have 5 points on them? So let me tell you that there are none. But how do you prove that there are no other lines? Okay, I mean, if I give you a polynomial time algorithm which is going to find all straight lines which pass through 5 of these points, it should somehow prove that there are no more. And I want a really relatively succinct proof, one that will sort of scale nicely with k. So this turns out to be the algorithm. This is somehow, we came up with it based on some ideas from coding theory, but it simplifies very nicely in the setting. So the thing that we will do is find an algebraic explanation of all 14 points. Okay, I'll tell you what I mean by an algebraic explanation in a minute. But the important thing is it will be of all the points. Trying to find an explanation which explains 5 out of 14 points is hard because I have to figure out which 5 to work with. But all points out of all, there's, n choose n is 1. There's no brute force issue here.
You want purely deterministic. You won't take randomized.
I won't be randomized in this. It's purely deterministic. And then I'll just stare at this algebraic explanation. This is the technical term that I need to explain to you. Okay? So let's see what's the algebraic explanation. Turns out that here's this equation, x to the 4 minus y to the 4 plus x squared minus y squared, and it turns out to be 0 for all the points if I assume this is the origin, 0, 0, and this distance is a unit distance, and this distance is a unit distance. Okay, and this is the plane. Okay. That equation is satisfied by every one of these points. Okay. So what am I going to do? I'm going to plot all the zeros of this equation. That's what it looks like. Okay, and now you can see that there are 2 straight lines in the picture. Okay. So what happened over here? What does it mean to stare at it? I mean, if you stare at it, you can see there's a circle and 2 lines, right? What is this notion of staring formally? It says you factor this polynomial that you're given. And it factors into x squared plus y squared minus 1. That's this circle. That's just some spurious data which was mostly errors, and I should ignore it. And then there is x plus y. Oh, that's a linear factor of the form y minus p of x, where p of x is a linear function of x. And this is y minus p prime of x, some q of x, which is another linear function. And these are the 2 straight lines that are explaining our data. And it turns out that this methodology is not something that comes up by coincidence. It always works. Okay. So I'll tell you briefly why these things happen. Firstly, if I give you n points in the plane, I can always come up with a polynomial whose degree is 2 times square root of n that passes through them. Okay. Why is it 2 times square root of n, not n? We all know that there's a degree n polynomial through n points in the plane. But there's actually, when I'm looking at 2 variables, x and y, and I'm looking at the degree as the sum of the degrees in these things, I get a lot of things, and in fact, it's very trivial to prove this. This is much easier than proving that there is a degree n polynomial passing through n points. And in fact, not only is it trivial to prove, it can be found in polynomial time. So an equation of this form is very easy to find. It's just found by solving a linear system. There's no guarantee over here that in fact there will be a unique solution. There may be many. And in fact, if your points all came from 1 degree n polynomial, degree k polynomial, there may be sort of many of those, and we don't know how to pick which one of those to pick. But it turns out it doesn't matter which one you pick, because this polynomial that you care for, the linear polynomials in these examples, or in general something of the form y minus p of x, will always be a factor of this polynomial, and polynomials can be factored in polynomial time. So this is some very nice work by Grigoriev, Kaltofen, Lenstra, and all in the 80s.
They're just assuming the 2D case or higher dimensions too?
Everything that I'm doing is for the 2D case. These algorithms are actually much more rich and work in n-dimensional case, but then the scaling with respect to n has to be measured very carefully.
That will go exponentially, right? All the terms.
Right. So they scale exponentially in the number of dimensions, the number of variables, but you have actually very tractable variations of the problem of these solutions even in those cases. So yes, but fortunately I won't get into it, because it's really something where it suffices for us to deal with the two-dimensional case. And in fact, if there was any innovation, it was saying, well, there was a one-dimensional problem that we wish to solve, and we concocted from it a two-dimensional problem which is much easier to solve, and that thereby we were able to make progress here. And this eventually led to a simple, efficient algorithm for correcting p fraction of errors, where p was actually going to 1. So doing vastly better than the classical 1960s algorithm, because those things were bottlenecked at P being 50%. They needed more data than errors. We can work with it even when that's not the case. Okay? So that's the conclusion of the first thing. I would say that over here there's a, so in general, the theme over here is that, now we have much more powerful computers available. We can do much more powerful, sophisticated encoding and decoding, and these can actually be leveraged. In particular, when you're working with, large alphabets, when you're transmitting symbols over, the English alphabet or things like that, then actually you can deal with a large fraction of errors pretty much in the optimal sense. However, there is a very fundamental challenge when you think about transmitting bits, where again the connection between list decoding, the adversarial error model and the random error model all hold, but what's holding us back is that we don't have good algorithms for recovering from as many fraction of errors as in the Shannon case. And if we could make progress over here, this would be a wonderful theoretical step. It would basically tell us that, look, we never need have worried about the probabilistic error model. We could always work with the adversarial model, which is completely safe and much, much more pessimistic as a model of errors, but it doesn't take away anything. So this is an important question over here, and something that I hope that if you're interested in, I can tell you about later. Okay? So I'll now try to move on and tell you a little bit about two vignettes, two more, and they deal with the other issues that we are seeing when we're talking about errors and computation together, communication and computation together, one of which is just a matter of scale. Okay? So how reliably can you store data as the amount of data scale increases? I mean, every day we are putting more and more and more stuff on digital storage devices, and we are constantly worried about the fact that, eventually we're going to have errors. The question is, how reasonable can we make the error tolerance? Now, this is a question that Shannon actually already encountered, and there was a question at that time saying, so as the amount of information that we are trying to store on some storage device or communicate through a communication channel increases, would this increase reliability or will it decrease it? Prior to Shannon's work, I think the general impression was eventually, either you have to give up and go to 0% rate of usage of the communication channel, or you're going to have very high likelihood of error. And Shannon came up with a very surprising answer at the time, and he said, no, you can hold steady at a fixed rate at which you're going to be packing information into your storage device, or packing information, sending information through the communication channel, and the reliability goes up as the length of the transmissions grows. So the probability that you will make a decoding error at the end goes down exponentially with the length of the transmission, which is very surprising. So don't we pay any price for the fact that I'm taking longer and longer and longer pieces of information and sending it to you? Actually, I do. And the catch is that, look, if I'm going to send you n bits of information, you have to wait for n bits of information to arrive. Then you apply a global decoding procedure which looks at all of these things and says, what was the right message that was transmitted to me? So the decoding time grows with the length of the data. It was growing exponentially with the length of this data that you were receiving in the Shannon decoding algorithm. That was eventually fixed, and we have polynomial time algorithms and even linear time algorithms now to correct all these errors, but we haven't gone below linear. Okay, so linear seems to be an essential thing. So more and more as the data grows, you're going to have to spend linear amount of time trying to figure out to maintain it reliably. And one question is this essential? And I think, I'm going to give you some theoretical interpretations of this question, but I think independent of the theoretical interpretations, this is an important question. Practically, this is a major, major, major challenge, and I wonder how we are eventually going to solve it in the future, because I have all my information on various forms of disks, and I would like them to be around when I die. So it's not clear how I'm going to be able to manage that. So what is it that we've learned in the theory of computation? What we have to say about this? Well, firstly, there is an emerging field of algorithms in the theory of computation. It's called sublinear time algorithmics. And these are based on the fact that algorithms do not always have to read the entire input. You can assume they have random access to the input. Maybe the output that they have to produce is relatively small compared to the input. Maybe you're trying to look at the huge amount of input and say, does it satisfy some property or not? And they don't have to have the usual exact guarantee. In particular, they might say, well, what I'm going to tell you is something that's true about not what you gave me, but something close to what you gave me. So if you allow for these three settings, then actually algorithms don't have to run in linear time, and then you can ask this question. In particular, you can apply this kind of algorithmic insights to the decoding problem. For example, the prototypical question is, I might give you a CD or a DVD and I say, well, does it have too many errors or not? Okay. For this, I don't need to have an exact answer saying, look, if the number of bits that are corrupted is 561, you have to say 561. You can give me a number saying, no, somewhere between 500 and 600 bits seem to be corrupted. An approximate answer suffices. And so even something simpler, I see errors in the CD, or actually this CD looks, pretty good, and I would suspect the amount of errors is much less than 10%. That kind of a coarse answer would be sufficient. And if an algorithm, if you can somehow come up with a coding scheme by which you can put the information on the disk, which allows you to answer such questions very efficiently, not by scanning the entire disk, I would call that a locally testable code. Okay. Similarly, you might ask the question, okay, here's the CD. I want to figure out what's written in this one sector and give me the answer quickly. Shouldn't have to go through the entire CD or the DVD. But at the same time, you should have reliability, which is sort of growing with the size of the CD or the DVD. If you introduced, a large fraction of errors, I should not be fooled by it. If all the errors are on this one sector, that should not be sufficient to corrupt it. Can we achieve such effects? And this is a question that somehow got raised in the theory of computation. This was not asked in these terms. In fact, it was guised under buzzwords called probabilistically checkable proofs or private information retrieval. People ask these questions, and they've come up with some very non-trivial results over here. All I'll say is that there's a lot of work. What it says is that many non-trivial trade-offs are possible. The first thing that you think of, that linear time must be essential, is not true. You can actually do a lot better, like maybe locality, the amount of time that you spend could be n to some tiny power where you're storing n bits of information and tolerating 10% of n adversarially introduced errors, and still you would all be doing this, and the penalty that you pay in the rate would be just some constant factor for any epsilon. Okay? So these kinds of things can be done, and these are actually relatively easy, and there are mathematically very, very, very deep results which sort of say that, look, you can do much, much, much more with more intricate constructions. I won't tell you more about this except to just sort of put it in as an advertisement for this line of work. Something that I think is interesting. It's interesting to see what we will be able to make of this in the future. In particular, I would love to come up with algorithms which, codes which are not much worse than what we currently use for CDs and DVDs, have the same kinds of rates, but have very, very, very local testing things. So maybe I should just be able to sort of take a constant size snapshot of the DVD and say, oh, this looks like, it's got too many errors, or this looks like it's clean. So those kinds of questions would be great. It may be achievable. Similarly, I would love to be able to take, these kinds of things. Decoding seems to be somewhat harder in this setting, but still it may be possible that I can take n bits, encode it as n squared bits, and be able to do all my decoding I want by looking at 10 bits. For every bit that I want to recover, looking at 10 bits of the corrupted thing may be sufficient. These are all feasible and possible in principle, and these are technical questions that we have not been able to answer. To me, the even bigger question is, so finally, what is the model going to be? What is the model that is going to allow us to somehow take all the CDs and DVDs in our home, the way we produce them today, which is incrementally. Today I produce one collection of video images, I store it somewhere. Tomorrow I take another one, store it somewhere. And about a year later, I would like to be able to say, well, all of those are still available to me. And somehow the security, the reliability associated with it somehow grows with the number of information things that symbols that I'm storing. I would love to see what is the model that will allow us to cope with this, because we are going increasingly digital, and eventually I would love to see that all this information that I've digitized doesn't get lost. Okay. So these are some very important questions, I think, and I think these are things that I worry about how to deal with. Okay, so Sanjay, I should wrap up at around 5 or? Okay. All right, so this brings me to the final part. This is work that we are currently doing now, and it's in contrast to other pieces of work like list decoding or the local error correction and local error detection works, which are being done by a larger part of the theory community. This one is something that just me and my student are looking at today. But this is, to me, actually the most interesting thing and a challenge, and to me this is sort of fundamental in that I think in order to address this particular challenge, we are going to need communication and computation to come together much, much more tightly than any of the previous vignettes forced them to. Here, what's the challenge? So here I'm considering a communication channel, Alice talking through the channel to Bob. Alice sends the sequence of bits, Bob receives that sequence of bits. Now you might say this is nirvana, there was not a single error in the transmission, we are done. But I want to suggest that maybe this is still not done. If the channel is perfect, it still doesn't imply perfect communication. If you don't believe it, go try talking to the next the person who's going to vote for the other party tomorrow. Okay, so there's always a certain intent to bits that we are sending. So imagine Alice sends this message saying to Bob, freeze, and Bob decides, that clearly says that he should sit inside the refrigerator, while Alice meant something different. So there's intention associated with bits. I mean, freeze was a collection of bits, but it meant something in Alice's mind, it meant something else in Bob's mind, and this difference in how you interpret a sequence of bits is a constant. This is never something that we can eventually resolve away. So the question is, how can we try to model this problem, how can we try to understand it, and then how can we try to work with it? Because eventually it's not the exact sequence of bits that are on the DVD that I'm interested in. In fact, if you give me the sequence of bits that corresponds to an MPEG file, I don't think I can do much with it. You'll also have to give me the MPEG decoder to go with it, or else I don't think I can play the thing. So what if Alice is trying to send some instructions like freeze? So I want to give a mathematical interpretation to the concept of an instruction, and a good one is that it's an algorithm suggesting a sequence of actions that you should perform. Can Bob try to understand the correct algorithm? And what happens if they're speaking in different languages? And here we can actually formalize this question quite nicely by saying, okay, natural language is a sort of a very, as a morass of complexities. But here, by calling them programming languages, it becomes a very precise issue. I have a programming language in my mind, which means every algorithm can be written in some finite string in this thing. You have a programming language in your mind, so you can write down an algorithm. Can you communicate that algorithm to me when you don't know what programming language I'm speaking in, or that I understand? This is the question that we've been trying to look at, and the reason I think this is important is really, if computing is going anywhere, it's going in this direction of increasingly networked, interactive communication. There's interaction between pieces of software, there's interaction between software and hardware, there's interaction between different pieces of hardware, and all of these interactions are getting increasingly burdensome. Every once in a while my computer just decides that it needs to figure out how to talk to some other medium, and so it says, okay, I will not respond to you while I figure out how to respond to these other messages that are coming through. So getting these computers to be able to talk to each other is time consuming, it makes my computer unreliable, sometimes it makes it insecure, and I would love to have a different model of communication which is more along the lines of how humans communicate. They are not constantly based on two parties which have perfect understanding of each other, but based on the fact that the two end players are intelligent, they are trying to come to evolve to a notion of understanding. So how do we reach that setting? What is that setting? How do we model it, and how do we try to attain it? This is what we've been trying to understand over here. I'll try to tell you briefly what some of our results are over here, how we try to model it, and how we try to what kinds of things we saw. So the naive thing might say that, look, the modeling should be that Alice wants to send some algorithm A to Bob, and let's try and see how she can communicate it. At the end, Bob should get exactly this algorithm A. Okay, nothing else will work. Unfortunately, it's very easy to prove in such cases that this can never be done. There may be some person called Alice who speaks in some programming language who is sending to us an algorithm called A, who looks from our point of view exactly the same, because I'm only getting a finite number of bits back and forth, looks exactly the same after any finite prefix of interaction as some other Alice, Alice prime, speaking some other language, who is sending us some other algorithm A prime. I will see exactly the same collection of bits. And in which case, how can I ever distinguish between the algorithm A being sent to me and the algorithm A prime? I cannot. So this seems like bad news, but actually I think this is actually really good news, because if you can't distinguish A and A prime, why would you want to do it? Okay, I mean, imagine you're a colorblind person, somebody comes along and says, look, there's red color and there's green color and there's, these things have all of these things. If it doesn't make a difference to you in your life, maybe you shouldn't care. On the other hand, if there is a tangible difference that you can measure and evaluate, then maybe you should try to understand what the other person is talking about. But then this leads to a very deep question, which is what should be communicated? How do you model this problem in such a way that you can actually try to communicate something concrete? This led to our work with the student Brendan Juba, and our assertion over here was that communication, especially when you have intelligent people communicating with each other, happens because the end players have some measurable goals. Okay, so they should, the goals should be explicit, but they're not always. And what are goals typically? Well, some part of goal is just control. Okay, I shout out a sequence of things to you so that you can do something with the sequence of bits that you receive. So maybe I send a sequence of bits to my printer so that it will cause the action of printing those bits or some impression of those bits on a piece of paper. That's a remote control action. I send bits, but it creates a physical action on the other side. Or maybe I buy from Amazon, which I view as saying, I type a few keystrokes on my computer, and then a few days later somebody delivers a box at my doorstep. Okay, so this is, I sent bits out and got some physical reward for it. And this changes the environment around me, and that's what I mean by control. But not all communication is like that. Some communication is actually purely intellectual. So maybe I'm just interested in learning something about the environment. Or maybe I'm just interested in learning. So for example, this lecture, I'm giving, I'm sort of streaming out a sequence of bits at you. Question is, what are you trying to get out of it? And clearly, it may not be some physical deliverable, but something that you're able to get. And also, what am I trying to get out of it? And so these are all goals that one can associate with communication. These are all interesting phenomena in the form of goals. And our hope is to be able to model these things in some concrete mathematical way and say, what is it that one could be trying to do over here? So what we did was we started with these kinds of examples and came up with one very concrete, crisp goal which we could understand. And this is the way complexity theorists typically tend to think about these questions. And the complexity theorist is always trying to solve hard problems. And so we decided, let's say Bob is trying to solve some hard computational problem. So it's a weak computer, maybe he's communicating with Alice, who's a supercomputer, can solve all kinds of hard problems. And what you would like to do is send her some instance of this problem that you want to solve and say, give me the answer. Don't give me the algorithm, just apply the algorithm to this particular input, give me the effect, the end product, give me the output. Okay? Maybe this is what I want to do, but now we have this setting where Alice does not understand me. And one of the big challenges over here in this modeling of this problem is try to understand how do you say, this problem cannot be solved if Alice is not powerful enough to solve the problem. If she's no more powerful than Bob, then why should she be able to help? But notice that it's not sufficient if she's really just powerful enough and is willing to solve a hard problem. She also has to communicate it to Bob. But on the other hand, I want to say that she communicates it. At the same time, I don't want to insist that she understands Bob. So how can we model the difference between being able to solve the hard problem and express and answer such questions, being helpful in the setting, from the setting which postulates that she understands Bob? So this was a modeling challenge for a while, and eventually we were able to come up with a very simple thing, definition, which is this Alice should be considered helpful if she can help somebody solve the same problem. Okay, doesn't have to be this particular algorithm called Bob, could be some other entity who's no more powerful than this Bob, but actually understands Alice's language. So this is this definition that we were able to make formal mathematically, and I can, you can look at our website for a paper with Juba, which tells us how to solve this, how to formalize this. And once we have this definition, we were able to say that actually Bob can use Alice's help, but only in a restricted setting. In the setting where he uses her help to solve a problem where he can verify the solution on his own. Okay? And this turns out to be a very fundamental bottleneck, something that I think is interesting. And in some senses it says that, look, I mean, there's a lot of cryptography that we've built based on the fact that we don't trust the other people that we are interacting with. But all of that is useful not only to solve problems of mistrust, but even in the weaker case where it's not that the other person's, I don't trust them, but really I'm allowing some misunderstanding between me and the other person. So imagine I'm trying to go out there, download Microsoft, some antivirus software, and try to say, well, this is going to help me solve the hard problem of determining if a computer program is a virus. But in the meanwhile, I upgraded my operating system from version X to version Y, and the antivirus system did not really know it. Now I have a setting of misunderstanding. I don't think the antivirus system is deliberately trying to fool me, but at the same time there is a misunderstanding. Our theorems say that under sufficient levels of misunderstanding, this is as bad as mistrust. We should really, really not trust things that we can't verify. And eventually you'll make mistakes if you are gullible over here. So in particular, if Bob wishes to solve some undecidable problem like virus detection, it's not verifiable, so inevitably Bob will make some error over here. He will eventually make some error over here. Not with everybody, of course not with the Alice who understands him perfectly, but with some Alices that don't understand him perfectly, he might make errors. And in particular, this implies that he doesn't converge to a learning of her languages as well. The process by which you check your understanding of Alice and validate it is happening through this verification scheme, and it will never be able to, if you try to use her help to solve an unverifiable problem, you cannot learn her language either. On the other hand, you might use her help to break into some crypto systems. Well, crypto systems have the nice feature that when you break it, you know it. And that's something that's verifiable. It's very hard to break in, but once you're in, you know. And there, it's verifiable, so Bob can use her help. And in fact, this ability to use her help becomes a vehicle by which you know you're learning her language. How do you know you're learning her language? Well, you're talking to her, getting her help, breaking into crypto systems that you have no right to be able to get into. Clearly, somewhere there's help coming in, that's you're learning her language. And finally, if you try to use her help to just do things that you could have done on your own, sort integers and stuff, it's verifiable, so Bob does solve his problem, I'm sorry, but it's actually trivial. So what it means is that he might be actually misunderstanding her completely, solving the sorting problems on his own and thinking that he's understanding her. And so this is not a good way to learn other person's languages either. So one should try to somehow or the other get into this middle situation where language learning happens, and we have other settings where we can do it. So there's a little bit of work that we're doing on generic goals, but I won't talk much about it. And let me just jump ahead to our conclusions. The three vignettes, I think, are telling us that there's many, many modes in which communication and computational complexity can interact with each other. Particular models of errors can be more complex, and we can deal with them with sufficient computational abilities, and we should. We do want to figure out a trade-off between this global reliability and local computation. There is things that are possible over here, but it would be great to see what's the working system that we evolve to in the future. And the meaning of information that needs to be really preserved, and I think all of these vignettes tell me at least that I think we really need to see a sort of a great merger between how we compute and how we communicate, and studying them together I think is sort of really something that's important for the future. Okay, thanks, I'll stop.
Questions? Questions from either of the remote sites?
Stand up.
Does anyone from Duke have questions? Yes, no?
Maybe you should ask, because he has a mic.
No.
Oh, I see. Questions from anywhere in the remote sites?
You hear me?
Yep.
I had a question or a comment going back to the beginning of your talk. Turing actually did explicitly consider communication to be noisy or unreliable. The argument he gave for finite tape symbols, alphabets, was that if you had infinite alphabets, the human eye would distort them and you wouldn't be able to tell some of the letters apart. So that's where the finite alphabet comes from.
Oh, really? I wasn't aware of this, and thank you for educating me on this. I did wonder about it. Should have probably read the original papers, but I didn't. But thank you for that comment. I think I'm definitely very happy to hear that this connection was made explicitly.
Hello.
Yes.
Question on list decoding. You mentioned the polynomial degree for two-dimensional points.
Yes.
It is twice of the square root of n. But the linear system that you mentioned is still size of n. So do we assume infinite precision representation of those polynomial coefficients?
Right. So we don't want to. This is not a solution that will work in the case of real or rational things because of numerical errors.
Right.
In Reed-Solomon codes, we're always working over finite fields, and so we do have full precision. Finite precision is full precision in those cases, and so in such settings, these algorithms work just fine.
Okay. Thank you.
Sure. Any other questions? All right, I guess.
I'm sure you're aware of the work of Orlitsky and Rocha on coding for computing, right?
Not fully.
So the problem there, I mean, it's dual to channel coding, it's source coding, but the idea is that Alice has a number of bits, Bob has a number of bits, and they want to compute, say, modulo 2 sum of them. But Alice can transmit only at a certain finite bit rate. I mean, naive solution is just for Alice to transmit at the Shannon optimum, and then Bob does whatever needs to be done. But on the other hand, the fact that they have this common goal of computing a function rather than transmitting a string actually allows them to communicate less.
Right. So I would say that this actually model goes back to the work of Yao and communication complexity.
Right.
And yes, indeed, if one decides, so I think that was part of our thing. I mean, in Yao's model already there was this notion of, Alice and Bob are not in the business of communicating just for communicating.
Right.
They want to compute some joint functions, but it was still prefaced on a common goal, common knowledge of a goal.
Right.
And we wanted to go one more step and say, well, and suppose they don't even know what the common goal is.
Right.
Each one has their own independent incentive. What would they do?
Right.
And that led to our.
There's something like that in control theory, at least going back to Witzenhausen from the 70s, about team theory and stuff like that, where they're looking at value of information for subsequent tasks, and each agent may have his or her own goals and.
Oh, I would love to find out more about it. I'm sure this will be good for us to know about as well. Yep. Thanks. Prasul?
I'm trying to understand what I'm supposed to learn from your talk. And you talked about 3 pieces of work.
Okay.
So there was something that was, you took 2 years to understand Elias's algorithm, LIS's algorithm, and you improved it, right? And with this algebraic representation of those points, right? So there was that one part. You started off with the duality, and then you just jumped into this particular algorithm. And I'm trying to see where you use the duality. I was trying, the duality between Turing machine is doing computation generally, but ignores noise in some sense in a generic way, and Shannon requires some complex communication.
I wasn't trying to use the connection between communication and computation. I was. I think one of the remote questions clarified this, but I was just struck by the fact that these two were somehow, the theories have been kept separate, and I'm looking at questions which are not keeping them separate.
So I'm trying to see where the unification happened. So did it happen in the first part of your algorithm at all? First part?
In each one of these cases, I think the barrier between the theories of communication and computation where, at least in the research community's actions, they were functioning as effective barriers. I mean, they were sort of slowing down the work. We did not explore throughout the 60s, the 70s, the 80s, and the 90s, and 2000. We did not explore the question of why we cannot correct more errors than 50%. Why? I don't think it was because we thought it was it was not because we thought it was useless. It was because we thought it would be too hard computationally. So somehow computation became a barrier from the coding perspective, saying, look, I have a limited collection of algorithms, which is all I will employ. When you were willing to change the algorithm, we got much further along. I think there's a similar phenomenon that's going on with this local versus global thing where we don't have ultimate solutions. But once again, there's the question of, of course, we just have to examine all the data before we start, asking questions like, are there errors and how can we fix them? And the answer is no, it's not, of course. It's really, this is a case where if you look at the good results from the theory of computation, you can see that there's ways around it. And finally, I think the final vignette, just to me, it's just completely sort of settles the case. Information is useful to me only to the extent that I can use it to do something else. I'm not interested in storing a lot of bits. I'm interested in taking those bits and processing them to do other things with them, maybe to understand them, to learn some new things from them and pass on my wisdom. So it's really not, no intelligent device is sitting around trying to aggregate information. It's typically trying to use the information to do things. And when we try to use the information to do things, it sort of automatically takes us from the setting of communication to that of computation, because processing.
Let me press on a little bit. Maybe I'm not understanding. But Turing machines to me were useful for two purposes. You could prove what you couldn't do. Basically for one purpose. You could prove the halting problem, or you could prove lower bounds.
That's
right?
I wouldn't agree with that perspective at all.
But okay, maybe not. But they are an encoding of universal computation, right? So where did you use universal computation in your theory? You use complex computation, you improved your algorithms, but I never saw universality anywhere. In fact, when you were talking about communicating between Alice and Bob, I thought maybe you will go and encode the algorithm, the language in a universal machine and decode that from that, but you didn't go there.
I didn't. It's buried in the details in the third vignette. The way Alice or Bob try to find out what the other person is doing is effectively trying to figure out what they could be saying inside their heads, and this involves a process of enumeration. Okay. They enumerate the other person, and by that process, try to understand try to come up with hypotheses on what they may be saying, and then use the verification paradigm to say that, look, I came up with a hypothesis and I was able to verify my answers, so it must be right. So my hypothesis is at least functionally right for this setting, or something went wrong and so clearly my hypothesis was wrong. So, but the enumeration is very crucial, and the fact that you can attempt to describe the other person by a finite number of bits is important in that particular vignette.
Can you also give me one example that involves only one of those fields and not the other?
One of those, sorry?
You said you're trying to combine communication and computation. I'm still trying to understand that.
Okay.
Can you give me an example that is only communication and no computation and vice versa?
So I think Shannon's original paper was a lovely example of...
But it has the decoder and encoder, that's computation, right?
Not in the way he was expressing it. To him, those were just two mathematical functions.
It was taken for granted that you could do it. It didn't matter to him how complex it was.
How complex it was, and the feasibility of the computation was something that he abstracted away. I think it's a wonderful piece of abstraction. In fact, one of the things that's said about Shannon's paper, I mean, just like I didn't read Turing's paper, I also didn't read Shannon's paper, but one of the things that's said about it is that he explicitly said, let's set aside the notion of the meaning of information while we try to figure out how to transmit it. Let's ignore the semantics of information. And I think it's a great piece of abstraction. I mean, we wouldn't be here sitting around talking about all of these problems if we couldn't communicate bits reliably. It's because we are able to do it so nicely that we ask the question, so what next? And yes, and so I think in those original cases, we were really interested in questions of the form, how can we, is it even impossible, in principle, feasible to do something without asking the question of, and is it sort of really a tractable problem that we are trying to solve? I think we were always mathematically sophisticated enough to put in some level of computability into things, but the complexity of what is polynomial time solvable was not always factored into the thing, and that's the aspect that I would like to.
One question, if you still have more time. We had Ivan Sutherland visit us a couple of weeks ago.
Okay.
And interestingly, he gave a talk whose title was quite similar. The content was, of course, very different. His talk was titled Communication-Centric Computing.
Okay.
And he presented more of an architecture, but he also proved some bounds on speeds and communication and so on, as making very basic assumptions like chips are generally two-dimensional and not three-dimensional and so on. The central premise of his talk, which is what people in the architecture community are increasingly agreeing with, is that communication, the progression of Moore's law has brought us to a point where communication is a costly action,
right,
whether in area on the chip, wires take area, or energy, or delays, right? And computation is increasingly being regarded as relatively free.
Right.
So I don't really have a well thought out question to ask you, but I'm going to pretend that I'm Alice and you're Bob, and we may speak a different language. But the point was, so if communication is more and more costly and computation is freer and freer, how does that impact some of your modeling and some of your understanding?
Right. So that's a great question. I mean, I think so. Firstly, I think the paradigms that you're seeing in computer architecture today are not very different from what we're trying to think about over here. I mean, increasingly we're having to draw lines between, so what we used to draw as a single entity, this is one computer interacting with another one computer. Well, the computer is sort of, we're trying to make it faster, which means we have to break it into smaller pieces, look into the interactions between them, and eventually, communication and computation are coming together right there. And the other thing that I would say is that, look, I mean, we don't have a sense of how to scale. I mean, so the big issues in multi-core architectures, for example, is we don't know how to scale a collection of slightly loosely coupled computing elements together into some huge thing which we can make sort of verifiably reliable, right? And there, I think there is some issue. We have to ask questions about how these, how do we deal with issues of scaling when we are growing the number of entities that are participating, growing the number of modes of interaction that they have between them. And I mean, I think in many of these cases, I think a principle that's going to emerge is that, what's verifiable is much more, we can rely on what we can verify, and we should try to keep that as a sort of a governing principle. And maybe the computing elements will compute lots of stuff that, in the interim stages, which we will bother not to keep track of, but then come back to the things, to use the verification later as a checking paradigm.
You should wrap it up here. Thank you very much.
Thanks a lot. Thanks.